Hello everyone, I am Shrey Kohli. I am an embedded systems intern at Emertxe. During my internship, I worked on a washing machine simulation project. So in this video, I will be providing you an overview of all the topics that I have learned through this internship, and also I will be providing you an overview of my project at the end of this video. So let's get started. So as you can see the table of contents, now we are going to discuss about the goals of internship. The goals of internship are to gain hands-on experience in embedded C programming and microcontrollers, to gain knowledge in embedded systems and simulation tools, implement real-world control logic and build projects like building washing machine using microcontroller. Now, we will be going to discuss about what is C programming. The embedded C programming is like writing instructions to a tiny robot, the microcontroller, telling it when to blink an LED, when to move the motor, and other functions. Embedded C is just like instructions being provided to a microcontroller. So let's get started with the topics. Firstly, we are going to discuss about data types. Data types are defined as the kind of data a variable can hold, for example, integer, character, or float. Modifiers. Modifiers are basically like an extension to the data types that change the size or the behavior of data types. Example, unassigned long volatile. Loops helps us to repeat a block of code using for, while, or do while until a condition is met. So moving on, decision. Decision make choices in code using if-else switch based on condition. Creation of header files store function prototypes and definitions in .h files to reuse code cleanly. User-defined data types. User-defined data types are very helpful as they create custom data types using structure, union, or type definition for better structures. In the project we have made, we have also used creation of header files that we will be discussing at the end of this video. So moving on, now we are going to discuss about what are embedded systems. Embedded system is a combination of hardware and software which is intended to perform a specific task. Based on the type of hardware system, they are being divided into two parts, that is, based on the performance and function requirements and based on the performance of the microcontroller. Based on the performance and function requirements, the embedded systems are divided into four subsidiary parts that are real-time, standalone, network, and mobile. Based on the performance of the microcontroller, they are divided into small scale, medium scale, and sophisticated. Now we are going to discuss about the based on performance and function requirements real-time embedded systems. Real-time embedded systems are the ones that respond to inputs within a strict time constraint. They are used in critical systems like airbags, pacemakers, and industrial robots. They can be hard real-time and soft real-time. Hard real-time refers to deadline is strict. For example, ABS in cars. ABS refers to anti-braking systems in car because braking is a hard real-time example and needs to be in-field process. Soft real-time. Soft real-time refers to occasional delay is acceptable. Example, video streaming. For example, if during video streaming due to internet lag sometimes there is buffering. Standalone embedded systems. In standalone embedded systems, they work independently without any external systems, perform dedicated functions like washing machines, calculators, and MP3 players. Moving on, we have network embedded systems. Network embedded systems are the ones that are connected to a network, LAN, WAN, or Internet, communicate with other systems or cloud servers. They are found in IoT devices, smart meters, and security systems. At last, we have mobile embedded systems. They are portable and compact devices, operate on battery power. Example includes smartphones, GPS unit, and fitness band. They are one of the most widely used mobile embedded systems. Based on performance of the microcontroller. Based on the performance of microcontroller, we have three subsidiary parts. Those are small scale embedded systems. Small scale embedded systems are the ones that use 8-bit or 16-bit microcontrollers, low cost and simple applications. Examples: remote controls, toys and automatic doors. Medium scale embedded systems. These are the ones that use 16-bit or 32-bit microcontrollers. They handle moderately complex tasks used in smart appliances and automotive controls. At last, we have sophisticated embedded systems. They use high-end 32 and 64-bit processors run on RTOS or embedded Linux, found in aerospace, advanced medical equipment, and industrial machines. Now we are going to discuss about what are microcontrollers and microprocessors. Microcontroller. Microcontroller is basically a mini computer on a single chip. It has everything built in: CPU, memory, RAM, ROM, and input-output ports. Designed to do a specific job at a time, like controlling a microwave or washing machine. It's small, cheap, and power efficient, perfect for simple, real-time tasks where fast, dedicated response is needed. On the other hand, we have a microprocessor. Microprocessor acts as the main brain of a computer. Only the CPU is present. It needs external memory and input-output support to work. Built for complex, heavy-duty tasks like running software in laptops or desktops, faster and more powerful, but also need more spaces, power, great for tasks that require lots of calculation and multitasking. Now further moving on, we are going to discuss about the project objective. Like discussed earlier, project focuses mainly on design, functionality, simulation of washing machine using softwares for coding and simulation. It creates header files and source files. Header files were discussed earlier in this video, that is .h files that are very helpful for coding. They also uses timers for tracking time left to complete the selected process, using different switches for controlling different operations in the machine. So moving on, we are going to discuss about the project requirements and the software used during the establishment of the project. To make this project, we used MPLAB XID, XC8 compiler and PixSimLab. MPLAB ID is used for coding purposes, XC8 compiler is used to compile the code, and PixSimLab is used for the simulation of the code. Now discussing it, MPLAB XIDE. MPLAB XIDE is a software tool by Microchip used for programming PIC and DSPIC microcontrollers. Like in this project, we used PIC microcontroller, so we used MPLAB XIDE. It offers a simple interface for writing, compiling, and debugging code. It is compatible with Windows, Mac OS, and Linux. It works with MPLAB compilers and supports tools like PicKit for programming. It is widely used in embedded systems development. Now we are going to discuss about XC8 compiler. The MPLAB XC8 compiler is a C compiler developed by Microchip for programming 8-bit PIC microcontrollers. It is optimized for high performance and efficient code generation. XC8 works within MPLAB XID and supports various features like built-in libraries, code optimization, etc. It helps to convert C code into machine code that the microcontroller can understand and execute. PixSimLab. PixSimLab is a simulator used for testing PIC microcontroller based projects without real hardware. It provides a virtual environment to simulate circuits, input-output devices, and microcontroller behavior. It is useful for learning and debugging. PixSimLab supports various PIC devices and works well with hex files generated from MPLAB XID and XC8 compiler. The use of hex file will also be shown at the end of this video. Now we are going to discuss about the design and the board selection. So as you can see the block diagram, in the blue color we have a microcontroller, in orange color there are inputs, and in green color the output is being displayed. So let's discussing about input. There are 4 inputs that are power on, pause and stop, navigation, and door status. To power on the washing machine we use FW5 switch. To pause and stop we use FW6. For navigation we use FW4, and for door status we use FW1. Power on is basically used to switch on power and off it. Pause and stop are basically used to pause and stop the timer. Navigation is used to navigate through the menu for different options that we'll be discussing later, and door status is used to show the door status that is being opened or not. Power on is shown by display. Pause and stop is also shown by display. For navigation, we use display to navigate through different menus and its items. Door status is being indicated by buzzer. For example, if a door is open, the buzzer will buzz its sound, indicate that the door is open and we need to close it for washing machine. So moving on, now we are going to discuss about the microcontroller. The microcontroller used here is the PIC16F877A. As in the diagram you can see that it has various pins that are used for different purposes. This is the particular type of IC being used. PIC board. PIC board is a powerful and user-friendly development platform built around the PIC16F8 microcontroller that is widely used in embedded systems education. It comes equipped with essential onboard components such as LEDs, push buttons, 7-segment displays, a 16:2 LCD that can be converted into 16:4, and various communication interfaces, making it ideal for hands-on hardware interfacing. The board supports in critical serial programming, that is ICSP, and works seamlessly with tools like MPLAB XID and the XC8 compiler, allowing students to easily write, compile, test embedded C programs. Additionally, it is supported by simulation environments like PiximLab, making it an excellent choice for learning microcontroller fundamentals, interfacing peripherals, and building small-scale embedded projects. Moving on, we are going to discuss about the PIC16FA microcontroller. PIC16F877A is a popular 40-pin microcontroller from Microchip's PIC17 family. It is widely used in embedded systems and automation projects. It features multiple input-outputs that are from port A to port E, each with multifunction capabilities like analog input, digital input-outputs, and peripheral control. The microcontroller also supports external interrupts, timers, PWM, and parallel slave port, that is PSP interface. Its flexible pin configuration and rich feature set make it ideal for a wide range of applications. So now we are going to discuss about the timers in PIC16F877A. Timers in PIC16F877A are essential peripherals used to measure time intervals, generate precise delays, and create waveforms. The microcontroller includes 3 timers, that are timer 0, timer 1, and timer 2. Timer 0 is an 8-bit timer counter with a prescaler used for basic timing operations. Timer 1 is a 16-bit timer with an optional external clock source, ideal for longer timing intervals and capturing events. Timer 2 is an 8-bit timer with a built-in prescaler, postscaler, mainly used for generating PWM pulse width modulation signals. These timers can be configured in various modes for use in applications such as delay generation, event counting, and pulse width measurement. So moving on, now we are going to discuss about the CLC coding in PIC16F877A. The CLCD stands for Character Liquid Crystal Display, commonly available in 16:2 or 20:4 formats. It is used to display alphabets, numbers, and symbols in embedded systems. CLC coding involves initializing the LCD in 4-bit or 8-bit mode, sending commands like clear, display, cursor movement, sending data characters to be displayed. It uses control pins like RS, RW, EN. RS stands for register select. It is used to select command data mode. RW stands for read and write. Selects read write mode. EN stands for enable. Enable hence to triggers data latch. Now we are going to discuss about the digital keypads in PIC16F877A. The digital keypads in PiximLab is the virtual interface that replicates a metric-style keypad commonly used in embedded systems. It allows users to simulate key presses and interact with the microcontroller program without any physical hardware. Each button in the keypad is mapped to specific input-output pins of the microcontroller, enabling realistic testing of keypad-based applications such as password, menu systems, or numeric input. This feature is especially useful for students and developers to practice and understand keypad interfacing and scanning logic. When used with microcontrollers like PIC16F877A, the PIC Genius board, the digital keypad provides a hands-on practical learning experience in a fully simulated environment. So now let's move towards the implementation of the project.
To start the implementation of the project, firstly we load the hex file. Now as you can see, we have to press the 5 key to power on the washing machine. Now the washing machine is getting on as we press the 5th key. Now the options are being displayed. Now to toggle through these options, we need to press the RB3 key, which helps us to toggle through the options being displayed. So now to enable one of these options, we need to long press it. Now we are long pressing the buttons, which helps us to enable this function. Now enabling it will provide water level functions. Now to navigate through the function, we will be using RB35 key. Now we will be using the medium for this, or you can be use high. So let's use the high one. So to implement this, you will be long pressing it. Long pressing a button will show SW5 is start and SW6 is start. Now start this key. So as you can see, now here the timer has started. Now to start it, this is the maximum time being shown. We can also pause it, and to show that if the washing machine is being open, we will be using the R305 key. We will start this thing. Now the timer has started again after the pause. Now this shows that the washing machine has started. At the end of this, we will be using a buzz sound that indicates that the washing machine program has completed. After 32 seconds, it will get off. Now this indicates that the implementation has been done. So now the project has been implemented. Now at last we will be discussing about the difficulties that we have faced during this project. Difficulties that we have faced are the understanding peripheral interfaces, complex timer configuration, configuring timers like timer 0, timer 1 for cycle timings and delay needed precise calculations, debouncing issue with push buttons during input from buttons, false triggering occurred due to bouncing requirements, software debouncing techniques, LCD display glitches, displaying string dynamics on a 16:2 LCD caused glitches due to improper use of delay and initialization sequences, memory limitations. PIC16F8 has limited RAM and memory for storing multiple strings messages. So at last, the conclusion that I am going to share is, during this internship, I learned the importance of PIC microcontroller and various softwares used for coding and simulation, learned the use of embedded C programming and different types of embedded systems required and their usage, came to know about the integration of different nodes and microcontrollers and coding of different software with one another. So this was my whole journey. Also, I would like to share the coding files. It's taking a little bit time. So these were the files that were used in the washing machine program, that are the washing machine definition function, main.h, clc.h, isr.c, digital keypad.c. Firstly, we created the header files, and then we created the 4 files which helps in the implementation of this project. In the header files, we created clc.h, digital keypad.h, main.h, timers.h, washing machine.h. All these header files were useful by implementation of the main program that were the sources files being used. For example, for source.hed we use clcd.h, and for digital.h we use digital keyword.h. In these source files, all these header files were being used where macros were defined. For example, if I show you the clcd.h, here all the macros and functions were defined. For example, clcd put character, clcd print, clcd write, which helps in the implementation of the program's implementation. For example, we define the hex file here, and then we define functions such as clcd.write, static void input display controller, etc. like void print display put character and print. Similarly, in the digital keypad, we define all the macros, we define keypads, and we define all the switches and their implementation. Like for this, we use the chart that was given to us. And in the main.h, this is the heart of the header files, as it contains all the header files and all the macros that we'll be using in the main.c. Main.c is basically the file that contains all the information and all the functions that we are going to implement, as we seen in the simulation in the pixim lab. And especially in the washing machine definition.c, the main thing that we used was the cases. As you could see, as we had seen in the pixim lab simulation, that many options were given that we navigated through SPWB. So this was the coding done at the backend for the implementation of this project. So this was the whole thing. Thank you everyone, hope you enjoyed the video.